This session is It Just Networks, the truth about iOS's Multipeer connectivity framework. And Alban Decay is going to tell us about it.
All right. Thanks. Hi, everyone. So thanks for coming in this early. So my name is Alban. I'm currently working at this company called Data Theorem, where I'm doing iOS research because we're building a scanner for mobile apps, a security scanner. And before that, I was a consultant at Isaac Partners, and I worked on a bunch of tools that you guys may have or not have used. And so today, I'm here to talk about this new Apple technology, which is called Multipeer connectivity, which is pretty cool. And so, first of all, I'm just gonna describe what it actually is and like the kinds of problems it's trying to solve. And then describe how I reverse the protocol because it's all undocumented. So describe how it actually works behind the scenes when you're using it. And lastly, once we know how it really works, I'll briefly talk about the actual security of the protocol and the kind of assumptions you should make as a developer that's using that technology. So multiple connectivity. So it was introduced in iOS 7. And so it's a new framework, so a new Apple library that you can use as a developer. And what it does, it lets you write an app that can find the same app running on nearby devices. So you can find nearby devices and then start communicating with them and exchange data. So it was introduced in iOS 7. But what's kind of interesting is it was also introduced in the next version of macOS. So macOS Yosemite, which will be released in a month, now also has that framework. And as you can see on the picture. So I'm just going to do a quick demo just so you guys get an idea of what it is. All right. So on the left, there's a real iPad. On the right, it's the iOS simulator. And so I just launched a simple multiple connectivity app, as you can see, and it's an app to exchange messages between nearby devices. And so the first thing you have to do when you're using that is make your app yourself visible to other devices that are around, as you can see on the right. And once you've done that, again, devices that are nearby can find you and connect with you. And so on the left, on the iPad, I'm just going to browse for nearby devices, and it's going to find the simulator. And so once you actually decide to connect to the device, you get a prompt, as you can see on the right, which asks for confirmation whether you want to accept that connection or not. And so in that case, secret iPad. And if you accept, then the two devices are paired with each other, and now they can start exchanging data. And so as you'll see, I can now exchange messages between the two devices. And so write text. It's in the sample app, it's text, but it can be any data, and you can also exchange files. And what's really cool about it is it's peer-to-peer, so no need for internet connectivity, no need for cell signal. It's just finding nearby devices using peer-to-peer protocol. So it's pretty cool. There's one app that's kind of famous now that's using it. It's called FireChat. And it's kind of like this one. It lets you chat with people around you. For example, when you're in the subway or wherever. So it finds people that are around you and you can chat with them. So that's it for the demo. So it's pretty cool because it's very easy to use as an app developer. In like 10 lines of code, you can have something like that. So it's pretty slick. But so the reason why I wanted to do some research on it is that it's completely undocumented. So there's documentation on how to use it, but when you actually want to know how it really works, there's nothing. So for example, the first screenshot is when you start Googling for internal strings and constant, and you get no results. And then the other thing is there are security settings you can use. So you can specify which encryption you want, and there's also authentication. But since you don't know how it really works, it's hard to tell how these security settings work. So overall, because it's all undocumented, it was interesting. And so I ended up, having a look at the protocol and try to figure out how it works. And that's what I'm going to talk about now. But before I get into the details, there's two things I need to mention so you guys can get a better understanding. So when you're using the Multipeer connectivity framework as a developer, there's two security settings you can specify. There's the encryption preference, and there's 3 levels: optional, required, or none. And that's a screenshot from the documentation. So you have to specify which encryption you want, and that's all you get in the documentation. There are no other details, the kind of algorithm that are used, or how it works. That's really all you have. So that's the first security setting, and the other one is authentication. So you can enable authentication. To do that, you have to, in your app, you have to specify an identity, which is an X509 certificate, and a private key. And so that's going to be your app's identity when it's pairing with other devices. And the other thing you have to do is also write a callback. That's going to be called when you have to validate the other person's certificates as they try to connect to you. And so that's authentication. So 2 security settings, encryption and authentication. And the default settings are optional encryption and no authentication. And so back to reversing the protocol. So the test setup I had was exactly what you saw in the demo, so a real iPad. And then the iOS simulator with that sample app that I did have to modify, but similar setup. I only looked at the Wi-Fi. So something I didn't mention, it uses Bluetooth or Wi-Fi. And you don't really get to choose as a developer. It just tries to find the best thing. So I disabled Bluetooth because I didn't want to have to sniff Bluetooth. So my study was only on Wi-Fi. And so when you want to start reversing a protocol, the first thing you're going to do is look at the packet capture. And so when you do that with Multipeer connectivity, what you're going to see is that there are 4 different protocols, and 2 of them seem to be well known, and Wireshark is able to identify them and figure out what they are. And there's like 2 mystery protocols where Wireshark doesn't know what it is. And so what I'm going to do is briefly talk about the 2 protocols that are well known. But if you want more details, you can just look it up online, and there's tons of documentation. And then I'll spend more time on the 2 proprietary protocols, because that's the more interesting part. And so the first protocol you'll see is called Bonjour. It's an Apple technology. It's used to find services on a LAN. So for example, it's how your Mac finds a printer and things like that are on the LAN. And so that's what Multipeer connectivity is using to find phones around. And so your app basically advertises a Bonjour service, and you just have to choose a name for that service. So for example, for the FireChat app, the name that shows is FireChat. And so now the FireChat app is going to advertise its Multipeer connectivity service, and then nearby devices can find it. And so once they find that service, they get the IP address and the TCP port to connect to that service. And that's why the next protocol, which is unknown, is over TCP, and it uses the information that the app got from Bonjour to actually connect. And so when you look at it, it's definitely plain text. And so the few things you have to quickly notice is, so at the beginning you can see the names of the devices, secret iPad, iPhone simulator. And then something you can see is bplist00, which is the magic header for a binary plist, which is an Apple file format to store key values. So there's like the XML, you can write it as XML or as a binary plist, and that's what's right there. So looking at the protocol, so the first 2 things, each peer exchange what's called their peer ID, which is their name, iPhone simulator, plus some kind of random string. So, 123 G something. That's a peer ID. And then they exchange 3 p-lists. So again, p-lists are key value pairs. The first p-list is, so it's sent by the peer who's initiating the connection, and it has a bunch of keys. The ones that are interesting are the peer ID key. So it sends its own peer ID key, which is that iPhone simulator string I just talked about. So the sender peer ID key, and then it also sends the recipient's peer ID key. So they can sort of make sure they are talking to each other and not someone else. And once that's done, that's when you get the prompt that you saw in the demo. with the name of the other guy who wants to connect. And if the user says yes, then B sends back another plist. One thing that's in it is whether they accepted the invite or not. So yes or no. And lastly, there's a third plist that's exchanged. And the key thing here is that they're exchanging something called the connection data key. So each peer is sending to the other guy their own connection data key. And that's actually the main payload of that protocol. That's the whole reason why that protocol is happening is to actually get there and exchange that connection data key. And so that payload is briefly mentioned in the documentation. It's called connection data. But of course, they don't tell you what's in it. So if you actually have a look, it's pretty interesting. So the first thing is, in byte 1, you have the peer security settings. So whether authentication is enabled and the level of encryption. So they're all packed in a byte, so it's a bit field. And so that's what that byte is. So 5 means authentication enabled and no encryption, for example. So it's just the security settings. There's no certificates yet or anything like that. So that's one thing. And then there's a list of candidate IP addresses, and I'll define candidate after that. So a list of IP addresses, so 192, 168, 18, etc. So a list of IP addresses, which are the peer's local IP addresses on all network interfaces. And then some kind of IDs, and I actually have no idea what they are, but if you look at the debug logs, they're called IDs. So to be investigated, and then also port numbers. So basically, that connection data key is the peer's list of local IP addresses and UDP port, and it's being sent to the other guy. And the reason why it's doing this, so it's exchanging candidate UDP sockets. And so the next protocol, which is called ICE, for interactive connectivity establishment. So that's a well-known protocol. And what it does is from a list of candidate IP addresses and port numbers, it's going to do connectivity checks to try to find the best network path to the other guy. And so that's why in the previous protocol, each peer exchanged their list of IP addresses, and now ICE is going to use that to find the best network path. And in the debug logs, that's what you see. So it lists all these addresses and port number, and then it's going to send packet to see which one works best. And if you want more details, again, it's well documented, so you can look it up. But once that's done, then each peer knows an IP address and a port number to connect to the other guy over UDP. And that's where the last protocol comes in. So it's something over UDP. And so when you look at it, Wireshark has no idea what it is. And it does not seem to be plain text, as you can see. And that's a protocol that's used when you actually send messages. So as I was doing in a demo, sending text messages, that's where they are, but obviously it's not plain text, so it's kind of intriguing. But you can sort of, when you're looking at the framework, you can sort of guess what it is, because one thing I briefly mentioned is when you use authentication, it's going to use SSL certificates, external certificates. So that's kind of a clue on what it should be. And then if you actually set a breakpoint on an SSL function, so SSL handshake, which is Apple's SSL handshake function, the breakpoint gets triggered right in that protocol. And if you look at the stack trace, you can see that function, GCK session perform DTLS handshake. So that pretty much gives it away. So that's DTLS, but it's very strange because Wireshark knows how to parse DTLS. But in that case, it's not working for some reason. So kind of strange. So what I ended up doing was looking at normal DTLS protocol and see if there were any differences. So at the top is that protocol, and then at the bottom is when you use the OpenSSL command line tool. And so if you stare at the screen long enough, maybe you'll see it. But so basically, the first thing you see is 16 FEFF, which is 16 is the beginning of a DTLS record, and FEFF is the version of TLS. So FEFF means DTLS 1.0. So that's there in the mystery protocol. But then there's a difference, as you can see, which is there's a byte at the very beginning, D0, which isn't there in like normal DTLS traffic. And so if you spend more time looking at that, and also, so that seems to be the only difference. And if you actually go ahead and remove that byte, it turns out you can edit packet trace with a text editor, which was new to me. So if you remove that D0 byte using search and replace, then Wireshark is able to parse the packet trace and figure out that it's DTLS. So basically, the mystery protocol is DTLS 1.0 with D0 appended to every DTLS record. And it doesn't matter which device you're using, which version of iOS or anything, it's always going to be D0, which is kind of surprising. And I don't know why it's there, but it does break every TLS tool ever created. So kind of annoying. And then if you actually look inside the DTLS stream, it's just a really simple plain text protocol where when you send a message, like I was doing in a demo, you just see that message and the other guy's peer ID, and that's it. So it's very simple. And that's it. So that's the whole stack. And when you're reading the documentation, they mention two things, the discovery phase and the session phase. And the discovery phase is these first three protocols, and the session phase, where you actually exchange data, is the last one. And that's it. So now I'm going to talk about how the security settings I mentioned, how they affect the whole flow. And so as I said, there's 3 levels of encryption, none optional required, and authentication, which can be enabled or disabled. And so when you change these settings, the only thing that get affected is actually the last protocol, GCK2. And so if you look at the first combo, I guess, so encryption required with authentication, what you get is DTLS, and it's using mutual authentication. So each peer exchanges a certificate. And then, so what's kind of interesting is it has 30 different cipher suites enabled, including cipher suites that give you perfect forward secrecy. But the problem is that perfect forward secrecy is actually never used because in practice, when the peers actually choose the cipher suite, they're always going to choose the same one, which is RSA with AES, which doesn't have perfect forward secrecy. So PFS is enabled, but not actually used. And overall, they don't really need 30 different cipher suites because the client and the server is always going to be multiple connectivity. So it's not like you need IE6 to be able to connect to that. So they could probably reduce that to maybe 2 cipher suites. But I mean, overall, it looks pretty good. You have authentication, and you actually do get that with DTLS. So no surprises there. If you look at encryption required without authentication, you get DTLS, but this time it's using the anonymous cipher suite. So no certificates are exchanged. That's how these cipher suites work. So of course you're vulnerable to man-in-the-middle attacks. Still no surprises there because when you set these settings, you did specify that you didn't want authentication. So you're vulnerable to man-in-the-middle attacks. So it's kind of expected, but it's good to know how it actually works. And then encryption none. So without authentication, it's just that plain text protocol I just briefly mentioned. So no DTLS. So it's plain text. Again, no surprises because you said you didn't want encryption, so you don't get encryption. Then with authentication, this one is kind of interesting. So you get DTLS with mutual authentication, but it's using the null cipher suites, which are cipher suites that don't encrypt anything. So as you can see, RSA with null SHA. So basically, you have authentication, but all the traffic is plain text. Again, that's kind of what you asked for, so no surprises there. But now, the more interesting one, so encryption optional. So the documentation says this session prefers to use encryption, but will accept an encrypted connection, which is kind of interesting. So the first case, without authentication, it's basically doesn't matter because you don't have authentication, so you're going to be vulnerable to man-in-the-middle attacks anyway. But the more interesting case is when you have authentication and encryption optional. So as I said, the documentation says prefers to use encryption. So the assumption there is that if you have authentication and the 2 peers have encryption optional, they're going to actually switch to encryption required. And that's what this sentence imply, because they prefer to use encryption. But so in reality, so if you go back to how it all works, and this diagram tries to show you what's wrong. So you have bonjour, and then they exchange their security settings. And this is all before authentication. It's all plain text. Then ICE, and then finally the DTLS handshake. So there's something that's kind of wrong with that. Because the security settings are exchanged before authentication. So if someone is doing a man-in-the-middle attack, what they can do is change these security settings as they're being exchanged. And so they can basically downgrade encryption optional to encryption none, and do that for the two peers. And so now each peer thinks that the other guy doesn't support encryption. And so when you do that, then you get DTLS with no encryption. So basically, the traffic is still authenticated, but it's plain text, so you can see all the data. You didn't need to have a certificate to impersonate anyone. You didn't need anything. And now you can see all the traffic. And the problem here is that what they should be doing is, after authentication, they should check that the security settings that were exchanged at the beginning are what they thought it was. So they should make sure, oh, you sent me encryption optional, that's what I received, and they can confirm that what they sent was what the other guy received. Because if that's not the case, then someone changed the settings on the way. But they're not doing it, so you have a downgrade attack. And so when you do that, then that's what you see on the network. So it's DTLS, as you can see with the D017FEFF, but then it's plain text, so that's the test message. So that's unexpected. That's not what the documentation says, and you probably shouldn't use it because you're vulnerable to downgrade attacks. And so overall, most of the security settings, they work as the documentation says, except for the one I just described. And even without this one, there are combinations that, as an app developer, you shouldn't use. Encryption optional, there's no good use case for that. Because data is, it's sensitive or not sensitive, but it's not optionally sensitive. So I wouldn't use encryption optional. And then encryption none with authentication means you're getting the performance hit of DTLS because you have to do all the handshake, but then no encryption. So it's kind of a waste. And lastly, only, as expected, only encryption required with authentication is actually secure. So if you go back to that small table, you shouldn't use all the dark cells because there's no good use case. And then the red and the orange one are vulnerable, but if the data is not sensitive, then it might be okay to use that. So things Apple could do to improve the framework. One is prioritizing perfect word secrecy for when you use encryption, because they're already enabled but not being actually used, which is too bad. So prioritizing that. And then for encryption optional with authentication, which is the downgrade attack I described. So there's two options. One is they should, either they should validate the security settings as they were exchanged, validate them after authentication to make sure, again, what they received was what the other guy sent. And if you think about it, so SSL2 has a similar issue where in SSL2, someone in the middle could force each side to pick a specific cipher suit that was weak. And in SSL3, they fixed that by doing exactly that. So after the authentication happened in SSL3, each side exchanged a hash of all the previous handshake messages to make sure they saw the same thing and that no one was trying to mess with the traffic. And better, I think, so a better option, I think, is to just remove encryption optional, because I don't think there's a good use case for that. So there are many things that I didn't have time to talk about, so I'll put more stuff on my blog and also a tool. And that's pretty much it. Thanks, everyone. Are there any questions? Yeah, so the question is, what's the default setting? So the default setting is optional with no authentication, which is, so yeah, they should remove optional. No authentication as default is kind of expected because you have to deploy certificates in your app. So Apple could take care of that, honestly, but so. So the question is it used by the handoff feature that's in iOS 8, where you can start writing an email on your phone and then switch to your Mac? Yeah. I actually don't know. So one thing I looked at on iOS 8 was HomeKit, which is that framework to send messages to home devices. And in that case, it was not using this. For handoff, I have no idea. I haven't checked yet. Yep. So the question is, when Apple uses that, what are the security things they're using? So I don't know any Apple thing where it's using this, because AirDrop is not using this, as opposed to what people claim. AirDrop is different. So I have no example of an Apple app that's using this. So I looked at it. I think they're using the default settings. So the question was, which settings is FireChat using? But FireChat is not really. They don't have to care about security because it's an anonymous chat app. So there's no need for like strong authentication because you don't even know who you're talking to. So they're fine. Yes. No, so the question is what happens when you have encryption but no authentication? Sorry, authentication but no encryption, that's what you get. So it's DTLS, but it's using that no encryption cipher suit, which no one uses for good reasons. And so that's what you get on the network. So there's a DTLS record, and inside it's plain text. So it's HMAC'd. You can't modify the packets or do anything like that. Yeah. So I can't really hear you, actually. Okay. This one? Sure. So let me go back a bit. So when you look at the documentation, there's two phases: discovery, which is how you find nearby devices, and then session, which is how you exchange data. And so the first three protocols here are part of the discovery phase. It's all about finding the same app running on different phones around you, and then exchanging some settings to then finally establish an UDP stream with that device, which is the thing at the end. Yes. Developer settings. So the question is, these are all user settings. So there are settings you set when you write your app as a developer. So as a developer, you have to decide what you want to use. The user has no control on that. So the question is it using Bluetooth by default? I don't know. So it's going to either use Bluetooth or normal Wi-Fi or peer-to-peer Wi-Fi, which is an Apple peer-to-peer thing. How it decides which one to use, I have no idea. I think it just tries to find the easiest thing. So I think it would go for Bluetooth first, I'm guessing. But I haven't really looked at Bluetooth, so... And they don't give you the choice as a developer. You cannot say, oh, I want to use Bluetooth. So it's all transparent. No, you can't. So you just say, I want to connect to nearby devices, and you don't know if it's going to be Bluetooth or Wi-Fi or... All right. Thanks, everyone.